Head on Fire is a Patreon-supported podcast. Supporters of the show get early access to ad-free episodes, a private Discord server, archives, and more. All benefits are offered on a sliding scale, so no matter your level of donation, you never miss out. If you like this show, consider supporting it with $1 a month or whatever you can at patreon.com/headonfirepod. Thanks, and enjoy the show. Okay, so you are probably looking at the title of this episode and thinking, didn't he just put an episode out about quantum physics with like an expert in the field from Caltech? And like, yes, you would be correct. But one, around here, we don't think that one expert represents the end-all be-all of all knowledge. And two, your boy does ask multiple people, multiple experts. I had been wanting to have someone on to discuss quantum physics for a while, and I had actually reached out to quite a number of different guests who are all very, very, very busy professors and educators who have incredibly busy schedules, especially in the fall. I just somehow lucked into two of them saying yes to me. So that is how we are getting today's episode, which I really like, because today's guest, Caroline, is an expert who wears a lot of different hats, just like our last guest. But she uses her social media platforms to talk about multiculturalism and finance and, from time to time, quantum physics. So we're going to get into her professional qualifications. She'll go into all of that in the interview. But I just have to say, I found her from a video, like a semi-viral video, where she had stitched Hank Green and talked about quantum entanglement using socks. And it made it click for me in a way that very few explanations of quantum physics have made things click for me before. And I was like, I have to have you on my show. I am begging. So I reached out, she said yes, and she is here. So without further ado, here's Caroline. Caroline, welcome to Head on Fire. Thanks so much for being here.
Thank you. It's my pleasure to be here with you, Dawn.
I am
You're
so
awesome.
excited to speak with you. So I discovered your whole platform whenever you stitched a video with Hank Green, the inimitable Hank Green, to help explain a bit of quantum physics to him. And I said, oh, I have not understood this concept until you said this. You have such a relatable way of speaking about quantum physics. So, but I know that that's not sort of your primary, that's not the primary purpose of your platform. So yeah. So for folks who haven't experienced your content before, tell folks a little bit about yourself and what you do.
So I'm a gigantic nerd, and I just happen to be a very intercultural person, because I'm not a third culture kid. I'm the child of two third culture kids, and it makes things a bit, complicated. So basically I talk a lot about interculturalism and what it's like to, grow up living in different social settings, and how to navigate that. Also, what is the etiquette like when you're in contexts that you don't even know? How much can they differ from one another? And so, I give snippets of my daily life when I travel, or things that happened to me when I was in a different country. And a lot of people can relate, because, we're kind of an invisible entity, multicultural people, but we're totally here. A lot of people just don't realize it because we blend in so well, because we learn to code switch, right? So-called. And so I try to, raise awareness on the existence of people like me. But sometimes, since I'm a gigantic nerd, I will talk about other things like science. And I did physics at uni. That's where we're having this conversation. And the reason why I love science was because throughout my life, changing all of these continents and all of these languages and all these social things, science was the only consistent thing. And for me, it was a place of solace. However, I don't talk about it often on social media, because I also feel the weight of the responsibility of accuracy, right? And in fact, we can totally start with what I said in the Hank Green video, Stitch, and what went wrong with my metaphor. I can already rectify it.
Oh, so, sure. I love it. So it was about quantum entanglement, right? Correct, or something like that. Correct. So you said, I was telling a friend about this the other day. You said, okay, so when you have a pair of socks fresh out of the dryer, you put one on your right foot and the other one inherently becomes the left sock. No matter where it is in the universe, it inherently becomes the left sock. And I was like, It does.
Right. Another good example is you flip a coin. If
Mm-hmm.
it comes up heads, it's obvious that the bottom is going to be tails, right?
Mm-hmm.
Now, the problem with
Unless
this,
you are the DC villain Two-Face, in which case the other side is also heads.
oh. So if I start explaining to you what quantum mechanics is, what quantum stuff is to begin with, we will get to why this is wrong. But it's simply because it's supposed to be both of the same and not
Mm-hmm.
one is a thing and the other is another, right? But it's the idea, what I tried to explain through that metaphor is the idea of how they communicate. Because now, due to the new, Nobel Prize for Physics, a lot of terms have made their way into social media that people are deeply misusing. Terms like quantum entanglement, wave collapsing, qubit, spin. And I thought, you know what no one has ever done before? It's approached this topic from a literary perspective and a historical perspective. And I thought, you know what, this is the best way to teach it. So if you want me to, we can get
Of
into what it
course,
is.
absolutely.
Right. So first of all, I'm going to ask you a question. What do you think the word quantum comes from?
I'm gonna say Latin, and
Yeah.
I'm gonna just leave it there. It sounds like it's a plural. It doesn't, if it ends in isn't that a plural?
Well, not necessarily,
And
but
then
like,
and then I don't.
do you have other words that sound
Five?
like
Is
it?
it
Yeah.
like quint five? Does it
No,
have
no, no.
any
In
relation to
English, do
nutspace?
you have other words that begin with that?
I can't think of any, and I know a lot of words, but I can't
Right,
think of
right.
any words that start with that.
It's because in our brain, these two things are so disconnected, right, that you
Mm-hmm.
don't make the clap. And it's quantity and quantification,
Oh my gosh.
right?
I feel
Right.
so dumb. I'm sure
But
somebody
but
somewhere in a minivan is screaming at their speakers, going, "Oh, duh, it's quantity."
there's always people like that. We're both on social media. We know what it's like. Bestie, I feel you, right? So anyway, it's quantity. And the reason why I want to tell you this is because the reason why they use quantum to begin with is not really why they use it now. But I'm going to tell you how we got there because, you're in physics in high school and they teach you about like the motion of the pendulum. And then you get out into the world and you're like, what are physicists doing? And you get quantum computing and field theory. And you're like, what is how did they get there? It's actually super easy. And it has a lot to do with chemistry, to tell you the truth, right? So I'm going to start with one guy called Niels Bohr, my favorite physicist. This guy was whack, okay? He was, and we're talking about the 1910s, because we tend to think of quantum physics as recent things. No, we're talking about beginning of the 1900s. This guy was the professor of physics in Copenhagen, and he was famous because he would like climb buildings. But so people would like call the police. There's a guy climbing the bank, and the police is like, "Oh, that's just Professor Bohr."
I feel like that's why I know that name, Niels Bohr.
He's wild,
the climber
okay?
guy,
yeah, super famous. Anyway, he began doing these experimentations where he saw that basically, and the model of the atom, right? You have a nucleus and you have the electrons going around it. And he noted that when you give energy to the electron, it like changes orbit, okay? It goes up one. And when it reverts back to its original one, it emits energy, right? And he's like, well, there must be like specific radiuses of these orbits where the electron is stable. It doesn't emit anything and it doesn't need anything to be there, right?
Okay.
And so he used something that's very common Newtonian physics, MVR, mass velocity radius of that circumference, right? It's like this is the momentum of the electron going around the atom, okay? Now, do you know what a vector is?
It's a line.
All right, good, fantastic.
Yeah. Okay.
So we see it as a little line with like a number in it, like an 8 with a line, right? Okay.
Yeah.
It's a mathematical tool. This, I think, is the best way to explain a vector. It's a mathematical tool to give you a quantity that has two parts to it. It's to give two attributes to a thing. So, for instance, if I tell you, oh, Dawn, are you bringing a cake? Yeah. How big is the cake? And you tell me a foot. I'll be like, are you stupid? I need to know if it fits into my fridge. Is it a foot diameter or is it a foot tall?
Sure.
Okay. You need to know that. And so you'll be like, no, like it's yay big. And I'm like, yay tall. And so what you can do mathematically is just draw a line on the diagonal and say, well, and it has this angle. Okay. Or you can say it's yay wide and yay tall. So it allows you to have two components, either the diagonal and the angle or the height and the width, and know how big the cake is. Okay. So it's a very elegant way to give you a number that has more than one component too, in this case. Because then you can have also vectors in like 3 dimensions for it, but we only care about the 2-dimensional ones here, right? So Bohr, okay. Let me see if I can find, I have a bit of material in front of me. Let me see if I can find it.
I love the source.
Managed to, this is actually from my chemistry book, because I told you it's this intersectionality between physics and chemistry, and it's called structure of matter. Okay. One of my favorite subjects ever. So what he showed with an equation was that this MVR, which is just the model of the vector of this, the motion of the electron, is equal to a number n. This n is going to be the most important thing of this entire conversation, times Planck's constant divided by 2 pi. Okay. So already 2 pi, if you put it on the other side, you get the circumference. You can see how things match up. I love physics because one of the things that you can do, I call it, or it's my term, it doesn't exist, origamiing the equations. You fold them in one way, you put things, and as you develop them and you change the view and you look at things and you pass things from one side to the other and fold them, you discover new things about the phenomenon that you're observing, and it's wonderful, right? And sometimes you put two things together that were one on one side, one or the other, and you're like, oh my God, this is the other thing, and I can substitute. It means that there's a relation between these two things, and it gets mind-blowing, and it's amazing, right? And so he found this by folding stuff. He found that you can get Planck's constant there next to this number n, okay? That n is what orbit the number 1, 2, 3, 4, it can be in the electron. So why is it called quantum? Okay. By this, he quantified all of the other things into something that is multipliable by an integer. So let me make this super easy. I have a box of Cheerios, okay? And I pour myself a bowl of Cheerios, okay? Are you going to care how many Cheerios are in one bowl of Cheerios, right? Or in what placement they are amongst each other within the bowl? Or are you going to ask me how many bowls of cereal do you want to have breakfast with your family? You're going to quantify it into numbers of bowls of cereal. So the word quantum, quanta, whatever, it's a quantity. So it's like a slice of cake is a quanta of cake. A bowl of Cheerios is a quanta of Cheerios. A box of Cheerios is a quanta of Cheerios, right? So you get a bunch of numbers where you don't really care or know what they are all together. And you say this times 1 times 2 times 3 gives me a quantification of the orbits, okay? So this is where we get the term. I love your face. It's like, oh my God, it's dawning on you. I love it.
It is. I need more things explained to me in Cheerios.
There you go. There you go. Cheerios is the best. So
it sounds like it's an attempt, and I'm gonna try to basically say back to you what I think I just heard. Yeah. It sounds like it's trying to sort of quantify possibility or quantify.
We're gonna get to that.
Okay.
We're gonna get to that.
Okay.
Right now, we're just talking about like bowls of Cheerios, right?
Yes, bowls of Cheerios.
So it's like, do I care how many Cheerios are actually in a bowl? And what the probability is like that they're all going to be like laying flat? No,
I just care that there's enough Cheerios to shove it in my mouth while I'm watching Love is Blind. For all intents
and purposes, I want to know the number of bowls, and that's it. Another good example would be, I have a container that I want to ship out, okay? And within it, there's an X amount of gold ingots and an Y amount of pillows. All I know is that the container weighs a ton. Do I care how many ingots versus pillow, what the ratio of ingots is, or do I just care that it weighs a ton? I'm not the one who's going to be receiving that. I'm just shipping it.
Oh, okay. I was like, see, I might care how much gold is in my.
Nah. So you're just going to ship it. So you only care about like the distribution of things, right? So that's that MVR. Like sometimes you don't know what we're going to get to Heisenberg in a second. You don't know.
I love the idea that we're dealing with numbers. We're dealing with a number
That is a thing.
we're dealing with a thing, and that it doesn't actually matter what's in the thing. I
Exactly.
love that. I love that kind of like vague storytelling of math.
So I'm just gonna jump the gun. I'm just gonna jump the gun. I told you that we no longer mean quantum in that way necessarily, right? But we still kept it. The basics of quantum physics is calculating mathematically things that are not certain, things that inside you don't know, things with duality, and that duality gives you an uncertainty, and you calculate things taking into account that uncertainty. That's what it is.
The thing that one of the few things that I feel like I was able to absorb from my last conversation with an expert in quantum physics was that it's a calculation of the possibility that a point could be anywhere at any one time.
We're gonna get there. Let's go with the story. We're still in the 1910s. We're still in the 1910s. So Niels Bohr, he's our bestie now. Niels Bohr is our bestie. He made, due to this discovery, right, the fact that he could, put a relation with Planck's constant with this, etc. It was the true beginning of quantum stuff. So he quantified the motion of the electron around a nucleus. He did so many an enormous, gargantuan amount of work. He published it, calculations, whatever, only to find out that all of this only works for hydrogen. Isn't that heartbreaking? So another guy called Sommerfeld came up and he's like, I got your back, Niels. Okay, don't worry. We can account for more electrons if we, this N, I'm sorry, I jumped the gun on myself. This N became to be known, okay, as the principal quantum number, okay? N, principal quantum number. This guy, Sommerfeld, was like, I got your back. The only way in which, they can't share the same space clearly is if we put the orbits in ellipticals, okay, elliptical form. So he added this other number called L, which is how squeezed the ellipsis is, okay, how squeezed it is, the eccentricity factor, right? And so this new L is the new quantum number, a second one to be added to that one, which is the angular quantum number, okay? But that still wasn't enough because another guy called Zimmer, okay, he was like, well, look, it's still an electron. So if we take some copper and we coil it and we run a current through it, so a bunch of electrons, this creates a magnetic field. It's called an induction coil, right? If you put a piece of metal within it, it will magnetize it. And he said, we're dealing with very small things, but still. So no matter how small it is, an electron turning around something is going to create a magnetic field. And we need to account for that. So they added another quantum number, and it's called the magnetic quantum number. Okay, so now you have three parameters already that you need in order for a lot of electrons to be around and stable around an atom. But then finally, they were able to show experimentally that, yes, there is a quantum, there is a magnetic field, okay, produced by the electron through its orbit, okay? And I think this was proved by people called Stern and somebody else. It was two scientists, right? But finally, they managed to see it, but they saw that it is disrupted. It's not uniform. And the only thing that could account for that mathematically would be if the electron was also spinning on itself. Right? So this was posited by two guys called Goudsmit and Uhlenbeck, and you probably never heard of them. These are the only famous name thus far is Niels Bohr, okay? And they said it must be spinning on itself, and they calculated that the only ways in which this could be either clockwise or counterclockwise, they express it mathematically as plus or minus 1/2, okay? So it has this duality. Right, so now you have four, and this became known as the quantum number of magnetic spin. That today we call the spin, okay? Now, these four are the four quantum numbers from like the Jurassic of quantum mechanics, right? Until this guy, now this name you should, I hope you know, because he's really famous, a guy called Pauli. Yeah, it's one of those, it's niche, but it's famous, okay? It's niche, but it's famous. He came up with something that is called the principle of exclusion, where he said, Okay, none of these can be the same for two electrons. Like you can't, you need to have at least one of these numbers be different if it's more than one electron. They cannot share the same properties in same space, right? Now, I want to show you the horizon a bit. Can you see, right, when we're talking about wave collapsing, qubit spin, whatever, can you see on the horizon how if two particles are exactly the same in all of its motion properties, magnetic field, whatever, so you make them really close to each other, you entangle them, then at the end, the thing that is going to have to be different is one of them.
Right.
Maybe the spin, you know?
Sure.
All right. So you can already see how they started to see this, you know, binary applicability to it. But still, it was really in the early stages, right? What happened at one point? What year was it? We're still talking about like the 1920s, right? But this was what shook it all. A guy called Louis de Broglie, okay? Imagine, like, because this was the vibe to it. This guy called de Broglie opens the door, is like, guys, guess what? You know how light has like a wave particle duality? Newsflash, all particles have it.
Is this the thing? And I'm going to ask a stupid question because we're probably not there yet, but is this the thing where observers start coming into play?
In a second,
things operate one way when we look at them and a different way when we don't.
We're opening the door to that. Yeah,
okay.
We're opening the door to that. Yeah. Because that's another thing, right? That people are like don't really get, like observing and how it interacts. And
that was something else that kind of blew my mind. That observers, humans like to center ourselves in all conversations. Generally speaking, like if you have a discussion about evolution, we will center ourselves as though humanity is the peak of evolution. Correct. And everything else, you know, we won that race. And all of evolutionary history culminated in our existence. We like to center ourselves in absolutely everything. Despite the fact that if you told that story from a lion's perspective or a jellyfish's perspective or a blade of grass's perspective, they would say, oh, so in all of human history, evolution went along and then we got lions or then we got jellyfish and then, you know.
That was so poetic, by the way. Evolution from the point of view of a blade of grass. I love
That's not mine. I'm pretty sure I cribbed that from Terry Pratchett.
Okay, well, a good person to crib from, let me say.
But it's so interesting that we do that in sciences as well, math as well, that we make it about us observing things. And what I got from another conversation was, oh no, a pen could be an observer. Anything could be an observer. So
let me give you an example. Oh God, I wish I had looked this up before. Wait, so let me give you an example. The experiment where this comes up the most is the two-slit experiment, right?
Yeah, the double slit experiment, yeah.
This double slit experiment, right? So, because there's a difference. This is something that people miss. There's a difference between interacting and interfering with the system. So we interact with everything, okay? Because even if I am, I don't know, looking at this pen, okay? Even if I'm not touching it, I am interacting with it because there are photons that are reflecting off of it at an angle and at a wavelength because the pigment refracts them that way, okay? And they're entering my retina and my brain is interpreting that signal as blue, okay? So I am interacting with it. It is touching me, okay? But I'm not interfering with it, right? So there are ways to interact with things and observe things without interfering with them. So while, you know, the Futurama joke, when they're at the horse races and the professor is like, no, you change the result by observing it. Okay. That's funny, haha, but not funny, correct physics statement. Okay. But like, it's true because it's a type of observation that interferes. Okay. Because sometimes that's what you have to do. This is the thing that I wish I looked up. So for instance, you use a lot of chemistry to do this stuff. Okay, let me go back a step. The problem that we have with physics and that we have with mathematics in general is the fact that we are limited by our human senses, okay? So if I want to observe an atom, it's clear that my eyes can't do that, okay? I'm gonna need, other stuff to do it. And so little by little, you also get the technology to expand your senses to do this. And the technology could be simply an escamotage, like a fun way, okay, to get around the problem that we have in observing. And here chemistry comes a lot into play. Or it is actual technology that allows you to see, like a microscope, okay? So you use pre-existing physics to help you with that. Or you develop new mathematical tools, okay? Mathematics is an amazing tool because you discover things through that you couldn't before when you origami the equations. But I'm answering like 5 things at once. Let's try to get little by little about like what is the observer, right? Let me get to the observer, right?
Yeah.
So what you do is develop things to try to interact with a system but not interfere with it. So when, for instance, they wanted to see if we receive neutrinos from the sun, how do you do it? Neutrino is a lepton. A lepton is a type of particle like the electron is, but it has like no charge. It has theoretically no mass. How do you detect it? How do you see it? And they made like underground these huge things with a lining that use like a chemical reaction to interact with the neutrinos and see if we were bombarded by them, because they're so small, they pass through matter. How the frick do you catch them? And so they use chemistry for that. So you have to develop
really tiny nets. Just really tiny nets. Really tiny nets.
Actually, they put a happy hour sign and they just stopped for a bit and then they fucked off.
Just hang out. And we just counted.
They just hung out. But one of them, I think, is in Korea and the other one is in Canada.
Yeah.
Not sure.
Yeah.
But like they were just hanging out Gangnam style, happy hour Gangnam style. So happy for them. But yeah, so the observer is not necessarily you, is that you use a thing. And for a mathematical perspective, you can totally use the pen as the observer. Because, for instance, if I want to say, okay, this is really cool, and we're going to get to the time question with this if you want.
Yes, I do. Yes, I have. I know that the way that I want to ask you that question, but please continue.
So essentially, mathematics, one of my professors said, the problem and point of mathematics is to know at what distance you're supposed to look at things. And from what angle? Because if you want to observe a basketball, okay, and you put it under a microscope, you're not going to know it's a basketball. You're just going to see like the surface of it, and you're like, what is this? And if you put it 1,000 miles away, you're never going to know. It's going to be a pinpoint thingy. You're never going to know. You need to look at it at the right distance, okay? This was my non-Euclidean geometry professor. He was amazing. I loved him. I absolutely loved him. So the idea is that you put things into a perspective that makes sense. So classical mechanics, right? I throw a ball at you. If this pen was here and I throw it at you, you're in front of me, this pen will see the ball do an arc. So when you say in physics, the pen as the observer, that's what you mean, okay? But I can also do a couple of fun things, okay? Because you wanted to ask me, do you believe in time? And it's not a matter of belief.
Right. So I think the better way of approaching that, and I think that we're getting to the point in the conversation when I feel like I can hear the listeners, and I want to advocate for sort of the listeners, like what the average Joe can get out of this. So what we talked about earlier, human beings like to center themselves in all conversations. So like when we talk about observers, we like to make ourselves the consummate observer. That and we strip the word observer from that beautiful explanation that you just gave. And we mean the way that we literally interact with the world, the way that we think about things, the way that we touch things and stuff like that. And people take that little nugget, the observer thing. Oh, well, when you observe something, you change the way that it behaves, yada, yada, yada. They take that, they dumb it way down, they take it wildly out of context. And that's how you get something like the law of attraction.
Can I give you another way to look at this?
Yes.
Which will give you the same conclusion, but I think this is a more accurate perspective. physics and science is a cumulative work of one dude putting down a brick and saying, this is stable here. And then another dude putting a brick next to it and be like, this is stable here. Then a third dude being like, I can put a brick on top of those two and it's stable there. And they keep on doing that until one brick is not so stable. So another guy is like, this sucks. I'm going to remove this and I'll find a better alternative. Here, it's stable. And you keep on doing that. And when people say that there's a logical fallacy in the scientific method because it is leaning on consensus gentum, so at the end, would you say that the truth is like democratically elected? No. You need to imagine to be in a world full of people that hate you and that as soon as you prove something, they're all striving to prove you wrong. And
Correct.
if your theory sustains
that's something I hate when woo-woo people start talking about the scientific method, because I'm like, no. You're ignoring falsifiability.
Exactly.
The entire point of the scientific method isn't to prove that something exists. It's to basically disprove it. You're trying to tear it apart.
And we're now converging to what I wanted to say to your thing, which is physics is something that you build bottom up. Okay.
Correct.
You have fundaments. It's a cumulative work. You cannot jump the gun. Okay. And this is why it's so also a bit frustrating to have to talk about quantum physics with people that don't know basic physics.
Sure.
Because you show it to them and you kind of make them get, do you know how many comments I got under that video with people saying, I now understand quantum mechanics? And somebody, bless him, answered, no, you understood a metaphor of quantum mechanics. And I was like, I was so here for it. But basically you build from the bottom up with a concept of solidity, okay, and falsifiability. And then you reach the peak of this conclusion. And what people like, the law of attraction people do is instead get that peak and say, I actually think we got there from here.
Right.
No, we got there from here. Well, I don't care about that. You don't care about it because you don't know it. Like there's reasons for this.
Right. And it's the people that got here because they think they understood 6 or 7 different metaphors, and they think the metaphors are a replacement for all of those layers of bricks.
Exactly. Do you know that I got one of those new agey people stitching my video, and he began saying, because she's saying that quantum mechanics is complicated. And, at that moment, I stopped watching the video because I was like, if on the dictionary, there could be an image under the definition of Dunning-Kruger effect, it would be his face, I'm done. Because this is the point. Scientists built from the bottom up, they take facts and from that they draw conclusions. People who instead get conclusions and then look for facts to back them up, not only is this thing like cognitive bias best friend, confirmation bias best friend, okay, this is what lawyers do.
Oh, sure. And
it's like the antithesis of a scientist.
And I think, another way of looking at that is that sort of time question. I worded it very poorly in my last conversation, but I think the better way of doing it is to say something like, once again, the way the general public who are not quantum physicists, who are not physicists, who the last time they took physics was maybe a semester 30 years ago or something like that, and they barely understood it. I took physics, I barely understood it. The only thing that I got out of it was my science professor took a penny and shot it through the ceiling one time with a device that I do not understand. So I majored in social science.
I love this.
But for the lay person, we do still get a little bit excited about science. I mean, we love technology. We're all addicted to technology. And, science fiction is all around us. Marvel is the biggest thing to ever hit movie theaters ever. We're bombarded by, nuggets of the word quantum here and there. And then you get headlines, like I sent you a headline just in the last year where it says, physics says time is not real. And it's like, does because I feel like there are people acting more or less in good faith, trying to report on
this is not in good faith.
Sure. But you do still get like some science reporters. I mean, you'll see some headlines in National Geographic, places that people feel like are more reputable organizations.
Correct.
That still have kind of clickbaity headlines just because that's where we are these days. To get anybody to read anything, you need a headline that grabs. And what grabs headlines? Time isn't real.
Correct.
Your
Correct.
thoughts impact the world around you. Like taking something, removing all context, getting a clickbait headline, and then the headline is the thing that's retweeted 7,000 times,
Exactly.
and people read the
Exactly.
headline and they think, okay,
Exactly.
that's it. That's all I need to know. Time is not real. My thoughts are things. The law of attraction is real, et cetera, et cetera, et cetera. And what I would like to know is, what should we as consumers of this, as enthusiasts of this, I
Right.
enjoy learning. I am a consummate curious person. I like learning. I am not ever going to be a physicist. My brain
Right. Right.
doesn't work for that. What should we be doing when we see those headlines? How do we parse out and find the context? And how do we find, like, what's the truth behind that? Or should we just look at that and say,
Okay.
you know what, it's physics, maybe I need to put that aside?
Well,
Maybe
okay.
that's not a
So
for me thing.
the truth behind that, I believe you told me that, like, in that article, they just said because every time doesn't exist because everything happens all at once,
Mm-hmm.
right?
Right.
If you want me to, I can make
Sure.
it so that we observe it so that everything happens all at once. So let's go back to the metaphor of the me throwing you a ball with the
Yep.
pen as the observer. Okay.
Okay.
Right. So if the pen is on our side, it's going to see an arc. Okay. But if I put the pen on top of us, bird's eye view, it's just going to see a ball going in a straight line.
Mm-hmm.
And instead, if I put the ball behind you, the pen is just going to see a dot going up and then down,
Mm-hmm.
you know, because I'm removing a dimension from it. Basically, time is a dimension. We see, it can't not exist. We observe it every time there's
Sure.
movement, right? Every time there's movement, it's time. It's there because it's meters per second when something
Mm-hmm.
is moving. That's velocity, right? It's just a dimension that we do not observe physically.
Consciously.
Okay, it's something a bit more abstract, but mathematically speaking, it is like our z-axis for a movement that is two-dimensional. Okay, like the movement of a ball in the air when I'm throwing it to you. So the only thing I have to do, right, is I put the time on the z-axis and I just make it so it's looking directly at you. And so whatever the hell is happening all at the same time because I just
So
deleted
that's what
that
it means for
axis.
everything to be
Yes,
happening at the same time. Not
correct.
that, like, 1742 and 5000 BC and
Happened
right
at the same time.
now
No,
and
you can
800 years from now
superimpose
are
it.
all happening at the same time.
No, no, no. It's kind of like, you know, those sculptures that when you look at them from a certain angle, it
Yeah.
shows a picture,
Uh-huh.
right? It's kind of
Yeah.
like that. It's kind of like that.
Okay, so it's just about the fact that different points of perception are all happening at the same time.
Or I'd rather think of it like, yes, but I'd rather think of it as through math,
Mm-hmm.
which is a tool that we can use
Mm-hmm.
to observe things. We can flip the situation around to the point in which we can actually observe a universe where time isn't a factor. And that's cool.
Well, and see, I feel like the best way that I have been able to understand that is in an episode of The Orville. Don't hate me.
Never seen it. I've never seen it. I don't even know what that is.
I've heard the science of it. Okay. But anyway, time travel had to be a plot point in a particular episode. But
Mhm.
since they were like, well, we want to try to make this scientifically accurate, they did it by traveling a really great distance in a very short period of time and
Okay.
then coming and then going back. And then that pushed
Okay.
them forward in time, like
Okay.
thousands of years or something. Like, going many, many light years and
Yeah, yeah.
seconds and then coming back. Because, or something like, the stars that we see are actually very, very, very old, even though we are
Yeah.
perceiving them right now. Like that distance, that, like what you were talking about, the perception, like the way of seeing something to be able to measure that distance, that great distance is sort of what keeps us from perceiving the actual current time everywhere. Am I making any kind of sense?
It's a bit whimsical, but yes.
Yes. So, well, like, okay, so my sociology brain wants to take what you said about different points of perception happening at the same time and turning it into the reason why it is so difficult to take witness statements when a crime has occurred, because if a crime occurs on a busy street and 30 different people see it, you're going to have 30 different stories of what happened based on that person's perspective. It
But
isn't
here's
that.
the thing,
Mhm.
there you don't have what are called impartial observers, because
Exactly.
people,
That's true.
what they
Yes.
will remember, because you have, human error in between, which is
Yeah.
your memory, the
Human.
trauma. Maybe if you see a crime happening, it might trigger something that is in your traumas,
Sure.
and you will superimpose the two things. So there's a bunch of other things happening here that are so-called non-measurable.
Mhm.
And what physics does, it's the science of things that are measurable.
Yes.
So actually, you know what? Now that I'm talking about this, you know what I find the most hypocritical thing about spiritual people that want to use physics as something that sustains whatever their belief is, oh my God, like the circular logic and how hypocritical it is. The entire premise of spirituality, it's that is something that exists in a non-physical realm, and
Sure.
yet they insist on using physics, which is the descriptor of the physical realm, to support that. But by their own definition, they're not even in the same realm.
I do have my biggest problem with the spiritual community. And obviously, I mean, I'm a spiritual person. I wrote a book about spirituality. I continue to operate in a spiritual space. I feel like I'm a woo-woo person, but I feel like what separates me from a lot of people is that I don't agree in inserting science or the language of science into your spiritual belief. I believe that if you want to believe something, because it enriches your life, you should do it because it enriches your life, not because you're trying to scientifically prove it. I feel like trying to scientifically prove a paranormal claim, a spiritual belief, something like that, I feel like it negates the purpose of belief.
Correct. And not only that, do you know what I find dangerous about it? Is that why would you want to prove it if not to convince other people? And therefore, that's gives me cultist
it immediately
behavior.
It falls directly into fraudster behavior. It falls into, I'm trying to sell you something. I'm trying to get you to believe, or maybe not sell you something. Maybe I'm not trying to take your money, but maybe I'm trying to take your time, your effort, your energy, something from you, because I'm trying to twist a bit of science nugget, a metaphor, a headline, a tweet. And I'm trying to take that and and extrapolate all this spiritual stuff out of it and get you to buy things from me because, oh, this crystal will align your quantum aura or whatever.
Exactly. So, if you believe in things, which I think that whatever belief doesn't hurt anybody else is legitimate and it's amazing, and I'll always support it. I personally don't have it. I'm a huge cynicist, but I'll support it in other people. I do have fun with things like, hey, what's your sign? It's great. But I will never, ever, ever say that science supports it,
correct. Because, tons of studies have been done where you give somebody their chart, but you lay out 12 different charts, you remove the signs, you switch them all up, and people have no idea which sign theirs is. But again, I think that the entire the fallacy of trying to prove belief with the language of science, not actually the scientific method, because if you injected the scientific method into it, you would have to include falsifiability. And what is the point of belief? It feels like if you want to inject that, I'm okay with it up to the point where if you have a belief or you have a claim or you have something that's maybe making you afraid, if you hear a sound in your house and you think it's a ghost or something, injecting falsifiability into it, helping to try to tear apart what it could be, whatever is left over after that is then worthy of your belief. But I don't think we do that. I don't think the spiritual community does that by and large. I don't think that we want to falsify it. We just want further evidence, further proof that we're right. And we want to be able to say, look at how science does it. I really love the way in which
you phrase this. I really loved the way in which you phrase that. Whatever it means is worthy of your belief. You're not saying it's true, it's objective, it's worthy of your belief.
It's worthy of your belief.
I love the way you put it. Yeah.
Thank you.
So where did we leave off? All right, so time, dimensions, whatever. Right, no, you know what? We're back at the history. We're at the guy who
Yes.
barges in the room and says, guys, guess what? All
Mm-hmm.
particles also have this duality.
Mm-hmm.
And people were like shook. And so here is what you will find a bunch of physics memes online where people say, yeah, because quantum entanglement and the spin, by the way, it doesn't actually spin, right? It doesn't actually spin.
Right.
And people are like,
Yes.
why,
I think
why,
you did a
why?
video about that, how we call it
Exactly.
spin, but it's not
But
spin.
it's
We just
not a
don't have another
spin.
word for it.
And the reason why this is, it's because the spin was introduced because of that interference in the magnetic field. Do you remember that? Right?
Mm-hmm.
The fact is that it's not itself spinning, it's the oscillation because it's a wave function. So when he says it has a wave particle duality, it's the fact that it's oscillating on its orbit that is creating that magnetic disturbance, not a spin. But you still use that. And by the way, if oscillation and spinning is still using like sine and cosine, it's using like your pi and stuff. And so the math is not that distant. Like it tracks, it tracks. Both explanations mathematically track, but this one is the one that is actually accurate, right? And now it opened up a whole bunch of things. So this is what we're talking about when we talk about the wave particle duality, the double slit experiment, blah, 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 right? And in the observation, you do what is called the function collapse. Now, before we get to the collapse, let's do this. In a quantum state, right? So it's a state where there is a superimposition of these two things, and it matters that they're superimposed, right? Because when you're in a macro scale, it no longer matters. No pun intended. It no longer matters because you're just using like classical mechanics. It doesn't matter. It's like when you calculate like me throwing a ball and you're like, well, air resistance is, it doesn't matter right now. It's so insignificant. You're not going to take it into account. That's the same thing. So here instead, wait, I got lost. ADHD for you.
Is the superimposition not mattering in the same way that the same way that the number of Cheerios in the bowl doesn't matter? Is it the same kind of not mattering?
Exactly. Now, what happens is this, about like a couple months distance, right? You got Schrödinger and Heisenberg simultaneously, I think Heisenberg was a couple months ahead, okay? Months, okay? They simultaneously developed two different approaches to the evolution of the quantum state. The evolution is when it hasn't collapsed yet, right? Okay. So what is going on there? And Schrödinger used differential equations, and Heisenberg used matrix mechanics. And they converged so well that Dirac then merged the two together. And that something is like bulletproof when two different idiots got to the same conclusion through two different methods. I love this for them. I love this for them.
That's the origami of the thing. If no matter which way you rearrange it, you come to the correct answer.
Exactly. Then Feynman also has a way of doing this, where he basically, you're talking about a trajectory, right? That these particles have. And he is able to substitute a single trajectory with like a sum of infinite trajectories. And then you can use Lorentz spaces and whatever. And this help for quantum field, other things, okay? Other things. But the point is this, is mathematical space. So, and this will give way into quantum computing, right? But I am jumping a gun once ahead. The collapse is simply the moment in which you observe a thing.
Mm-hmm.
With Heisenberg's uncertainty principle, you know that if you see the speed at which it's moving, you don't know the location and so forth. So the way in which these electrons are described is in these clouds of probability, which is what I think you got with your last interview, which I haven't seen, but you told me about, right? It's these clouds of probability.
Uh-huh.
And it's actually called clouds of density of probability, right? And it's, you can absolutely calculate this using those 4 quantum numbers. That is outdated now, but they still use it for eigenstates and eigenvalues, whatever. You do still use the M, the L, and whatever. And the collapsing is just the observation of it. And by observing it, you block the state of it into knowing that there's a part of it that you cannot know in that moment. you have one value, and by doing this, and if you can prove that it can be like the other thing, you do what is called the removal of quantum uncertainty. And so far you can't really do that. The fact that you're in a quantum space implies that you need to have quantum uncertainty, and that is the basics of it. The fact that you're calculating things, knowing that there are things that you cannot know, and accounting for it, and you can account for it with probability, mathematical probability. So the reason why people don't like this stuff on a truth level, it's because it removes all the magic from it. So imagine, you were mentioning Marvel before.
Sure.
Imagine if every time they slapped the word quantum on something to make it cool and, you know, mystical and whatever, you just said, oh, by the way, it's just because we're calculating it at a slightly higher level. It's a bowl of Cheerios and not the Cheerios, to make our calculations more simple. That's all. It's because they're going to be vibrating and stuff in it, and we don't really care. It's going to remove all the magic from it, right? And so
Sure.
I told you before we did this interview, I'm going to explain to you, and it will remove all the hype. It will remove all the excitement.
No, but I think that that's so good, because the only time we ever hear the word quantum anything, quantum entanglement, quantum mechanics, quantum physics, quantum computing, it either is in a movie where they're trying to just say the word science magic and they don't want to say it. It's why is Tony Stark able to do the time travel? Because he's in a living room and he's like, entanglement, quantum, and time travel. Or why is Ant-Man able to shrink down into the size of an atom and go fight Kang?
Quantum realm.
Quantum.
And it makes no sense. I love it.
But,
you see people, it removes all the magic. But it's one of those things, when you make one of those jokes, that it requires repetition, right? And so you repeat something and it becomes funny. Then you repeat it again and it becomes less funny. And then you keep on doing it until it stops being funny. But if you push it long enough to the point where it's cringy, it starts being funny again, right?
Yeah.
So, they say quantum, ooh, magic. You start to explain, you're like, not magic. But then if you push it long enough, you're like, this is actually unbelievably cool. And that's why
this
also
has
scientists
always been my argument
this.
For talking to experts in fields like this, because when you learn the truth of geology, when you talk to a geologist, when you talk to a geophysicist, all of the woo-woo stuff about crystals gets removed. And at first you're like, but then you start learning the deep down cool stuff about how rocks are made and what crystals do and what they act and how they're formed and all that. And that's so much cooler. The way stuff works is so much cooler than the woo-woo crap we come up with.
Look, the woo-woo people say crystals vibrate, which is absolutely not true, right? Because a crystalline structure is actually the most solid structure you could possibly have in chemistry.
Yes.
But imagine this, the fact that matter in general, the fact that entropy is something irreversible, right? Chaos is irreversible, and yet all systems tend to evolve into a state in which it's stable. And the fact that the most stable systems are symmetrical, it means that Bessie, the universe has an aesthetic. The universe likes order, and I love this.
I saw there was a video from another science creator on TikTok talking about how the universe is more like this complex 3D web thing the other day. And I was like, that is so cool and so scary to my tiny brain.
You know how cool it is that you see a crystal, as a scientist, you see a crystal and you when I look at it, I'm like, shit, the universe likes symmetry. And it's another person's like, oh, this is going to vibrate. No, it's not. No. Why? That's not cool. That's not even as cool as this.
Right.
It's you need to push it far enough. Unfortunately, it takes those steps, and people don't like steps. Especially when science gives you an explanation for something, and then, it's falsifiable. So they do falsify. They find a better way to explain it. But that way it's more difficult, more convoluted. And, you explain something to people and people get used to that belief. And then you come up years later and you're like, actually, no, it's this. And it's going to take a while for you to wrap your brain around it. They don't want to do it. We are also creatures of inertia, our brains as well,
Sure.
We got used to a thing, and having to reevaluate everything if it's not your main source of interest, or if it's not your mentality or your approach to it. It's, people in Spanish would say, ay, qué pereza, people don't want to.
But
and they get stuck there.
I think the one of the reasons why so many people kind of gloss over, and I'll be honest, sometimes the way that I learn is I need to be able to tell the story of something.
Mhm.
You know, algebra didn't make sense to me, but geometry did because I feel like I could tell more of a story with the shape of things and the measurement of the world around us.
Have you
Like that
ever read
made
Flatland?
no.
You should. A
Okay.
romance made with geometrical figures. It's a
But
novel.
I've read The Phantom Toll Booth.
I have not.
Well, then you go read that.
All right, fine.
It's a childhood fantasy about math.
I
Um,
love it. I'm here for
there
it.
there you go. But I think that so many people kind of tune out because they can't tell the story about how this applies to them. And I feel like when we talk about quantum, every time I hear an actual person that knows what they're talking about quantum physics, it's like even the quantum physicists don't quite fully understand what it is that we're all doing, like what this is for yet. Um, and therefore, one, it's easier to try to plug a woo-woo nonsense reason for it
Yeah.
exists. Oh, well, this tells us that, thoughts are things, or oh, this tells us that everything vibrates, or this tells us that we'll be able to teleport in 10 years, or something like that. Like they try to turn it into something applicable well before the science is there
Yeah.
for it. But the other thing is, I feel like the average person kind of listening to this goes, okay, but how does this impact me? What does this mean for me?
Okay, I'm gonna try and tell you what they're trying to do, what they think they can do with it,
Mm-hmm.
and why they haven't been able to do it so far, and why society is also to blame for this.
Okay.
So society is mainly to blame in general, because you need money to do these things. You need money for
Oh yeah.
development, right? If you look, like, for example, like at the development in the space sector, when was it that billionaires started investing in it? When there was a chance for luxury space travel. So you could have an income, right? So that becomes worth investing because you're going to have a return in your lifespan, okay? And that's why there's so much more money going into engineering, for instance, because if you invest in development in that field, you're likely to have a product that you can soon put on the market.
Mm-hmm.
With physics, this is not the case. The physics is so much more advanced than what we can actually produce with it, that you're not going to see a return on investment in your lifespan, right? So right now, this is the thing which I think is really cool, how they put computing into this, right? So computing in and of itself has always been the usage of things that are binary.
Mm-hmm.
So it's, how do I put zeros and ones, yes and no's, because it uses Boolean algebra, which is a set of mathematics, right? That it's a way of folding, right, mathematics, in such a way where you can do a number of calculations. It's kind of restrictive, but it follows very specific rules. And so a machine does essentially very stupid calculations really fast. Okay. That's it.
Uh-huh.
So the ways in which we managed to do this thus far is with this binary system. So, computers, they used to be punch cards,
Mm-hmm.
so you had either a hole or not a hole. And these were like the very first, programs. IBM started like this. Okay.
Yeah.
And then this developed into using zeros and ones, because what else can you use to do a yes and no type of thing? Well, electrons, it can be a negative or a positive charge. And so that gives you yes and no. It's very binary.
Okay. Mm-hmm.
With even microchips, they burn things, so you have like holes and flats, right? CDs also do this, the way in which they reflect the laser. So it's we've kept, like, all of computing is discovering ways in which to give zeros and ones to a machine to calculate. Okay. Now imagine you're a physicist and you are watching something, you're observing something, you're calculating something, you're experimenting on something that no longer gives you a thing that gives you a zero and a thing that gives you a one. You now have a thing that is both simultaneously. Can you see how appetizing that is?
Yes.
Okay.
Yeah, we talked about that a little bit with the video that we kind of shared with the quantum object or something that was both vibrating and not at the same
Yes.
time. Yeah.
Yeah. It has, because you can put it in the state where it's simultaneously both, right?
Uh-huh.
And it also has the capacity to be either or.
Uh-huh.
Okay. So this is okay. Well, I need to give you a metaphor because this is something that people like totally misrepresent. Okay. And this is where I screwed up with my sock metaphor. And I will use this to explain what entanglement is. Okay. If you have two mugs, one is blue and the other one is red. Okay. This is a binary system. And it cannot be green because this is the problem with the woo-woo people, right? When I'm saying I don't know the color of the mug, I'm not saying it could be any color of the freaking rainbow. I'm not saying it could be green. It can either be blue or I already know which colors the mug can be. It doesn't mean it can be anything. Not knowing the color of the mug doesn't mean it has the potential to be a unicorn. No, I just don't know whether it's blue or red in this moment.
Is this Schrodinger's cat? Is this the cat is dead or alive, but the cat can't be dragon?
Yes and no. Yes and no. It's okay. The correlation is not that immediate. Okay.
Okay, gotcha.
Okay. So you got the mugs, right?
Yep, I've got mugs.
And you put them into boxes. You put them into boxes. And I know as soon as I say box, people are like, Schrodinger, just stop. Put them into boxes, right? Because the idea of the box is that what connects it is the inobservability.
Gotcha.
Okay? I can't see it. I can't observe it.
Okay.
So if you give me, I know these two are boxes, and then you put them behind your back, and then you hand me one, I know that box has a 50% chance of containing a blue mug and a 50% chance of containing a red mug. Okay. And even if you give me the other one, each one has a 50% chance. So when it comes to calculating, I need to take into account that this one, yes, it could be red, but it could also be blue in equal amounts.
Okay.
Probability, not magic, not it could potential to be anything. Probability, okay? I need the woo.
And it's not a limitless amount of anything. It's a set quantity. It's a set quantity of things that it could be.
Exactly.
Yes, I'm here. I love it.
You're getting it. I love this. I love that I'm getting through to this. It's amazing. So what you're going to do when you want to entangle, two particles, is I'm going to get a bigger box. In one box, I'm going to put two blue mugs. And on the other box, I'm going to put two red mugs.
Okay.
So the problem with my sock metaphor is that people tend to interpret left and right as 0 and 1. You know, in this case, they're both going to be 0. They're both going to be my pair of socks. Okay. Mathematically speaking, so it uses a bracket system. It's a pun. Leave it alone. It's a pun. Dirac did this. Okay. It uses a bracket system called bra and ket, the two parts of it. Shut up. It's a physicist's sense of humor, okay? So I got one box with two blue mugs and one box with two red mugs, right? And so the two red mugs are the one red and one blue and the one red and one blue are singularly two different particles, right? But I only have one set with the two red mugs and one set with the two blue mugs, right? So if somebody tells me I picked a box and I'm going to give you one of the mugs and the other one is going to go to Dawn, okay? I suddenly look at the mug and it's red. I immediately know yours is going to be red too because they came from the same box. Essentially, if you have a 0-0 and I see that it's a 0 and I know that the only set from which my mug can be a 0, then therefore we're in the set where both are 0.
Gotcha.
Okay.
Gotcha.
It's not magical. It's not communication. It's math.
Gotcha.
It balances out because it's the only thing, you know, that explains that being that once you observe it, right? So this is interesting because you separate these two. And even if you're in the States, I'm in Switzerland, I know you'll have a red mug, even if we haven't talked. The problem, so basically we now have something.
So that's what the other guy was saying, there's what we do this calculation to try to figure out where this other thing is going to be. And once we know this, that's when we know where what that is going to. Okay. If he just said mugs, I'd have gotten it.
I mean, Mugs and Cheerios. Mugs,
Mugs
Cheerios, and
and
socks.
Cheerios, God damn
That
it.
should be the title of the video. What is quantum mechanics? Mugs, Cheerios, and socks.
Mugs, Cheerios, and socks.
I love it.
Mechanics for all. Yes.
Oh my God. So they decided to do this. So I have like this binary system now. Let's make it truly binary. And this is where vectors come in again. This is what they call the qubit. It's a quantum bit, right? That's why it's a qubit.
Oh, gotcha.
I love how much, if you just explain etymologically things, people would understand so much better because we use words for a reason. So the quantum bit uses vectors and probability. Look at this. So if I have a thing that has an alpha amount, okay, of probability of being a 0 and a beta amount of probability of being a 1, right? You can express that with, the cake is yay wide and yay tall. You can express that with a little
cake
vector.
after this.
Oh yeah, and cake. We forgot about the cake.
I'm gonna need some cake.
In the title, you need the cake, right? So,
yeah.
Yay amount and yay amount, you can express this with a vector. And the vector indicates, it's kind of like, a gauge thing. It indicates how probable it is that one is the one and how much is the other, right? That's how you use the little vector there. And you use it two-dimensionally, so alpha and beta, right? And 0 and 1s, okay? And so the probability is not like everything in between. We're not in the realm of R. So if somebody listening knows what set theory is, we're still talking integers and Boolean integers, so 0 and 1s, right? So it can't be anything between 0 and 1. It's like a probability of how much is a 0, how much is a 1, and you express that as a vector, okay? And they said, fantastic. I can entangle 2 qubits, and that's how you get the whole thing of the quantum entanglement with the 2 qubits. That's how you entangle them, okay? You get 2 vectors, you superimpose them, and this is what happens. Now, the problem is this. The type of information that is transferred, okay, is not classical information. It's quantum information.
Right. We're not doing 0s and 1s anymore. We're not doing simple dummy math.
It's things that are superimposed. It's things that are both simultaneously. It's things that have the uncertainty. It's things that have that. You're in a new kind of like mathematical realm, okay? And so the problem is the conversion from classical information that you want to send to quantum information. And the fact that you need to translate these two makes it impossible to make it faster than light. So the possibility is we either find a way to like communicate mathematically in a quantum way. No, we don't know. We can't see this insight on the horizon, or we find an easier way to translate this into classical information, where classical physics applies, right? Or, we have this obstacle. So on the horizon, we're still not sure how this can become a product, how this can become a way of information, because we have this obstacle that quantum stuff and classical stuff kind of need a bit of like a translation period.
I feel like this is probably so wrong. This is probably so wrong because again, I studied social science. I can take a survey like you wouldn't believe. But it feels like we're in the stages of figuring out gravity hundreds of years ago, just figuring out what even gravity is. And we're not to the point where we can fly yet. We're not to the point where we can then take that and say, okay, well, we know this, so then we need to be able to make something that gets us, at least lets us work with gravity for a little while or something. Do you get what I'm saying? Like we're still learning about this one concept way over here, and we haven't quite found the applicability out of it.
This is really funny. It's actually what happened with the Lorentz spaces in mathematics, and then Feynman used an application for it like decades later. It was insane. So, and it happens all the time in physics, which is cool because it's like a generational, millennial, not millennial as in millennial generation, like over millennia. It's an intergenerational collaboration that is so cool. I love it.
So I want to be respectful of your time. I know that we're running over and you're a very busy person, but I need to ask you, I just need to change. Do you mind if I change tracks just real quick? I just need to ask you, what is your favorite type of chicken pasta? Are you a chicken Alfredo girl? Or are you a chicken Parmigiana girl?
Get out. Get out. Blasphemy. You know what? That is something really funny, actually, that I want to talk about, how people want to interpret what they want to interpret, and you can put things like this one. So when I made the Italians don't put chicken on pasta video, the amount of comments that I got where all I said was, look, I know that in the States you have chicken parm, whatever, just so you know, and I know you call it Italian, just so you know, it's not Italian. And the reason why Italians don't put chicken in pasta is this, like cultural things, like customs and eating customs or whatever. That's it. The amount of people saying, are you telling me what I can and cannot eat? No. Or I'm still gonna eat it. Nobody said you can't.
It's just, if you came to my house, you wouldn't get that. You would get this other thing. It reminds me, your videos. So we have a multicultural household. My husband's Mexican. And, you know, I got to have a lot of food education early on in our relationship. We've been together over 16 years. And I remember one of the first things he was like, oh, fajitas are an American thing. Fajitas don't exist in Mexico. I was like, well, what are they? He's like, it's an American
Tex-Mex.
thing. It's a Tex-Mex thing. He's like, the closest would be just an actual taco. It would be. Have
you had tacos al pastor that they make? It's amazing. Amazing.
Oh, honey, girl. Not only have I had it, I can make it. I have his family. There's a few people in his family that have written cookbooks. Like, I mean, amazing. They are for real.
They're for real.
Offline, I'll send you the titles.
I want to share something about Mexico.
Yes, please.
Right? So, because, you know, different cultures have different applicability of things that I have from other cultures.
Sure.
Right?
Yeah.
So I'm going to reverse this for you, right? So the fajitas that are not actually Mexican, they're Tex-Mex, but they associate. I was in Mexico DF, and I went to a Sushito. Sushito is a franchise of sushi restaurants that is like...
Is it the sushi burrito thing?
No.
Oh, okay.
No, it's just called Sushito, and it's a franchise, and it's a sushi place, right? And they had it in Panama as well. So I was like, oh, it's in Mexico. I know this. Let's go to Sushito, whatever. They asked me, señora, ¿usted quiere salsa de soja normal o clásica? Normal or classic soy sauce? I was really confused. I was like, whatever, normal. They brought me a carafe with soy sauce with jalapenos in it.
What?
Yes.
That's Mexico. That's Mexico. That's listen, if you can't put a pepper in it somewhere, don't serve it in Mexico.
Can I say it slapped? It absolutely slapped.
I'm sure.
It was unexpected. But, you know, they at least don't pretend to be like original Japanese, like actual traditional Japanese. No. You know that it's like
so in America, that same story would go, oh no, this is actually we brought this over from Japan.
Oh my God, the parallelism with that. So there's so many people in the States that are so unaware of what culture actually is, and they keep on repeating things that they hear talking about cultural appropriation. That, for instance, if they see me, you know, I lived in Japan, I was engaged to a Japanese man, blah, 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 blah. If they see me wearing a yukata, they'll be like, you can't wear that. That's Japanese cultural appropriation. I'm like, it's summer. I'm at a matsuri. I'm wearing it correctly. Do you understand what cultural appropriation is or isn't? You know, it would be actually weird for me to go to a matsuri and not wear that. So it's this funny thing where people repeat things that they don't understand because it sounds about right. And
comment sections politics are a wild place I don't even know if it's good intentions. I just feel like it's just a constant desire to win a made-up war. Like they just all feel like they're soldiers in a war somewhere, and they're gonna zing ya. They gotcha. It's like
it's a search for the second Hegelian circle. You know, if you can't find a conflict outside, you're gonna have to find it inside somewhere. So yeah, you know, we yearn for it. So yeah, well, we've covered cake, quantum mechanics, literature, socks,
climbing buildings.
Climbing buildings, and Hegelian stuff at the end,
and jalapeno soy sauce.
tacos and sushi, you know? This is the way to go.
Sí, claro.
You know, if you can edit this last part out, it'd be great.
No,
like this last little
not
chorus.
at all. Absolutely not. This is what the listeners live for. Caroline, thank you so much for being here. I don't know that I hope I have a better understanding of quantum physics. At least I feel like I have a better grasp of how to learn more. I have a better language. I have a better vocabulary for it.
Yeah,
thank you so much.
My closing statement, I think, will be that, by the way, guys, this was unbelievably oversimplified with a lot of like tiny inaccuracies. It's to get you to wrap your head around it. Right?
Sure. So, but if folks want to engage with you on social media, where can they do that?
Well, you guys can find me on TikTok with my handle Zapithustra, and of course philosophy once more, right? And on Instagram I have the same handle if you want to write to me, but it will be like selfies of me and my friends going out to dinner. So it's like TikTok is where I put the nitty-gritty of it, like the
fashion game is on point, y'all have to see Caroline's fashion game. It is on point. Thank you so much for being here. I really appreciate it.
Thank you, Dawn. I love you so much. You're the best.
And that is going to do it here for this episode of Head on Fire. My gratitude to my guest, Caroline R.Z., also known as Zapithustra, all over social media. Go check out her content. It's great. It's hilarious. And there's beautiful outfits and food. And lots of stimulating conversation. So anyways, if you like this show and you want to support it, there are a number of ways to help. Consider sharing it with your friends on social media. That personal recommendation is the best way. That word of mouth is the best way to grow this audience. You could also like or rate the show 5 stars on Apple Podcasts or Spotify, and while you're there, leave a review. Reviews help recommend the show to other listeners like you. You could leave emojis, you could leave your favorite quote, just any review at all really helps bump us up in the algorithm. If you hate the ads at the beginning and end of this show, consider joining my Patreon on a monthly basis. Patrons receive additional audio and video content, as well as archived episodes, a private Discord server, and additional special goodies from time to time. You can sign up at patreon.com/headonfirepod. If you'd like to connect with me on social media, I am at HeadOnFirePod on your social media of choice. Thank you all so much for tuning in. I hope you had a very happy Thanksgiving if you are here in the United States, and I hope you're having a good November if you're not. Anyways, thanks so much for tuning in. Thanks so much for downloading the show. And remember that if you put a sock on your right foot, the other sock inherently becomes the left foot, and that is how Ant-Man is going to defeat Kang. Or something. Bye.